Okay, so welcome to our N3A seminar. Today, we are very pleased to have Professor Katie from University of Melbourne. She will talk about supernova explosions. Over to you, Katie.
Okay, awesome. So thank you again for letting me be able to talk to you about some of the things that I'm really, really excited about, in particularly these beautiful objects called supernova remnants. And today what I'll talk about is how we can actually use these supernova remnants to touch on essentially the properties of the star that died many, many years prior to seeing these beautiful objects. But because I know that it's pretty late where some of you are, and you're probably ready to go home or ready for dinner, I'll give you the quick summary or the key points of this talk today. So the key things is that supernova remnants are the long-lived structures of supernova explosions that are useful means to kind of test and constrain our understanding of how and which stars actually die. We can actually tie supernova remnants to their explosion origins and use their properties to understand many aspects of stellar death, such as the mass of the star that goes supernovae, how these stars actually explode and throw out their ejector into the environment, and how, for example, neutron stars get their kicks, and how, for example, magnetars may be born, and whether they're actually born rapidly rotating. And so this is only a fraction of the things that we can kind of do. So I'm always happy to talk more about other things and always looking for new ideas. So happy to hear from others. But of course, before getting into understanding what has been done, let's take a kind of step back and and start at the beginning. So one thing is that in the last few years, we've actually had a complete coming of age associated with our abilities to detect and follow up a wide variety of transients, including those that are associated with the explosive death of stars or with supernova explosions. With both current and future optical surveys, we expect this number to only increase as we enter the next era of data-intensive time domain astronomy with LSST, which will essentially now lead to a wide variety of interesting discoveries that will further our understanding of these and even other fascinating objects. However, even though our abilities to be able to detect these supernova explosions have significantly improved, unfortunately, they are located at such distances that we're actually not able to resolve the explosions very well, and it can actually be quite difficult for us to actually see the immediate surroundings of the stars that are exploding. As such, we would ideally want to detect supernova that have occurred much more closer to us to be able to kind of probe these properties and really understand the properties of the progenitor and exactly how they actually exploded. But unfortunately, supernova that actually occur nearby to us are actually quite rare. And in fact, even in our own Milky Way, we've only had 8 supernovae in the last 2,000 years, much less than is expected from 2 to 3 supernova per century per galaxy, which is what we expect for this current supernova rate in our local universe. And as such, this actually makes it difficult to study many aspects of the explosion directly. And so we really have to rely on other methods to do this. However, supernova remnants, the long-lived structures that result from a supernova explosion, actually provide us with a unique opportunity to try to study supernova explosions and their dynamics on much smaller scales that are inaccessible to us when we're observing supernovae in very faraway galaxies. More specifically, one of the most uncertain aspects of stellar evolution is essentially the link between the nature of the explosion and the type of progenitor star. So essentially what type of star actually undergoes the type of explosions that we actually see. And so as we know, it's thought that a massive star undergoes core collapse once nuclear burning has kind of led towards an iron core. However, the type of explosion that a star of a particular mass undergoes and the resulting outcome of this explosion, such as do we see an observable explosion, is a neutron star or a black hole formed, actually depends on a number of factors such as the mass of the progenitor, whether it's found in a binary, as well as the metallicity and rotation of the progenitor star itself. As such, there has been significant theoretical work to try and determine which stars undergo core collapse and produce a supernova of a given type, and which of those actually produce a neutron star or a black hole. And so observationally, there have been a number of attempts to try to identify the progenitor stars of core collapse supernova explosions. And what they do is they particularly look in preceding space and ground-based imaging or images that are available. However, this method is actually quite limited by a number of factors, including the supernova rate in the local universe and the depth of archival or even current observations that, were we lucky enough to actually have seen the star before the supernova was actually detected. And so as a consequence, really only a handful of supernova explosions have actually had detections of their progenitor stars. And with these studies suggesting that there is actually a deficit of high mass supernova progenitors above approximately about 18 solar masses. And you might have heard of this before, and it's called the red supergiant problem. However, even though we see that from the measurements of the progenitors of supernova explosions, theoretical studies of core collapse explosions actually predict that even higher mass stars should actually still explode, as we see here in the green vertical lines, which correspond to essentially different, where we actually have in the horizontal rows, we have different core collapse explosions here, while the green vertical lines are essentially whether we actually do see an observable explosion or not. But in these theoretical models, right, one finds is that, while we do see lots of green lines that are associated with an observable explosion, we do also see some parts where we don't expect to see an observable explosion, and that's shown essentially by what is in black. And so as such, it is possible that the lack of progenitors that are detected with core collapse supernova explosions or above 18 solar masses seen from the supernova progenitor measurements may actually just be a natural result of the fact that only a fraction of massive stars are expected to implode and form a black hole without a visible supernova. However, since we also expect observable explosions, right, that also fall into these higher mass range, the natural question that now arises is essentially, where are the core collapse supernova from those high mass stars gone, right? And so this is where supernova remnants can help, right? They can actually help us try to understand what the population or the masses of the progenitor stars that actually led to the supernova explosions, in particular, because we now know that there is an explosion there, and we can actually study essentially different properties of these objects. And so one way that we can actually probe the progenitor properties of supernova remnants is essentially by looking at the stellar populations directly around the supernova remnant itself. And so what we can actually do is use both essentially the age and mass of these stars, essentially as a proxy of the age and thus the mass of the star that actually produced the object that we're actually looking at. And so let's take supernova 1987A, one of the more famous supernova explosions. And what we can actually do is now look at essentially the star formation history or the properties of the stars around that supernova itself. And what we actually find here is that based on, we have here essentially is as a function of age, which is shown on the x-axis, and on the y-axis, we actually have essentially the star formation rate, so how much of that particular mass or that age is actually observed. We find that this progenitor should have come, or like this supernova explosion, should have come from a progenitor of about 15 solar masses. And this is actually consistent with other observations that we actually see. But even though this is one example, we do have to kind of understand essentially what is our expectations of our lifetime, or what we expect essentially to see in these type of properties or these star formation histories. And so what we need to actually look at is essentially something called a delay time distribution of core collapse supernova explosions, because this essentially quantifies our expectation of the lifetime of massive stars that we can then tie to the observations of the star formation histories. And so for single stars, you expect them to have lifetimes of around 3 to 50 mega years, while binary interactions can actually extend the lifetime of a star, while low metallicity environments can actually, which actually can help maintain rapid rotation of massive stars, can actually also extend the lifetimes of stars up to, say, 100 mega years itself. And so this kind of allows us to know what we're supposed to be looking for, or look for features that can kind of give us an indication of the type of masses of stars that we're actually observing. And so with this kind of idea already back in our mind, we can actually now use these delay time distributions to try to consider the star formation histories around supernova remnants. And so this is actually what we did. We looked at all the supernova remnants that are found in the Small Magellanic Cloud. And in particular, we did this because of the fact that it is the galaxy is face on. So we actually see the whole population of supernova in the galaxy. So that gives us a proper indication of the masses of explosion that occurs in this galaxy pretty well. And so what I can actually do is essentially here, I can then take one of our supernova, here where in particular, and just plot essentially the star formation rate as a function of time for this particular remnant. And what you may notice is that, of course, I've picked the one that is got a very distinct peak, because what this star formation history implies is that the stellar population around that explosion suggests that the progenitor was perhaps had a mass somewhere between 8 to 12 or 13 times the mass of the sun, and that this had intense star formation around 30 mega years ago, which led to this. However, I particularly picked one that looked very nice, right? But the problem is that these plots are not always distinct and beautiful and concrete as like what we actually see here. And sometimes we actually get something that looks more like this. So this is another supernova. And what we find is that essentially that in the local region, the region of the stars around it suggests that they actually have different bursts of star formation at multiple epochs. And so what that means is that it's harder to then say, yes, that this progenitor star was, this supernova came from, say, a progenitor star of, say, a given mass. And so in these cases, right, what we would actually have to try to do is assign a probability that, say, a given star of a particular mass or particular age actually corresponds to, is more likely or less likely to be the possible progenitor that we actually observe for that particular remnant. And so this is what we did. Essentially, we then looked at all supernova remnants in that galaxy, in the SMC, and then actually tried to associate a probability based on the star formation that it came from, say, a small, medium, or large massive star. And so we couldn't do anything much more precise than this because the limitations in the data that we used, but this at least gives us an indication of whether we do see more massive stars exploding or not. And then also, just to double check that what we were doing was correct or reasonable, we also tied this to independent measurements of the progenitor mass. So this is from looking at the ejecta distribution and independent constraints that one can actually derive from these objects. And so what the key thing is that we actually found that 22 out of 23 supernova remnants actually have a core collapse origin in the galaxy. And for each of these, we applied the probability distribution. And what you can actually see is that essentially the larger the circle, the larger the probability that this supernova arose from a particular mass. And so while you don't necessarily have to look at the details, what you may notice essentially here is that a large fraction of core collapse supernova remnants arose from progenitor stars that actually had larger than 18 solar masses, more consistent with maybe above 21 solar masses in the SMC. And so you might be thinking, well, maybe it's something special about the SMC. So the SMC is special. It is a very low metallicity galaxy. Is there some connection to understanding, is there some connection with how the properties of the galaxy actually affect the properties of the progenitors we see? And the answer is yes, we do see this. But we can actually, and that's completely another kind of discussion that we can also have. But the next thing we can actually do is let's look at another case, right? Do we also see this same behavior in, say, another nearby galaxy? And this is what we can actually do. And what we did is that we naturally then went to the Large Magellanic Cloud, so the LMC instead. And this is what my PhD student at the University of Melbourne, Sonia, has been working on. And particularly, we looked at the LMC because it actually has significantly more supernova remnants to be able to look at. And we can actually then do a comparison to see if we still see this behavior where we see more massive stars actually exploding. And so what Sonia did is essentially applied the same type of methodology that I presented before, looking at the star formation histories around all the supernova remnants and then connecting it to independent measurements of the masses that we get from other methods. And what she has so far found is essentially, again, the distribution of the masses that we expect to see from this study. And so again, here, the larger the probability that this arose from a particular mass, the larger the circle. But what you notice again here is that it does seem to be more distributed to the higher mass end of our mass distribution here. It's not as strong as what we have from the SMC, which we have some thoughts about why that could actually be the case. But what the key part here is that this seems to further suggest that high mass progenitors can actually produce successful explosions. And this is in contrast to what we see from just looking at particular progenitor measurements prior to explosion from the supernova explosions themselves. And so this is quite a nice, powerful way to actually understand how stars actually died and what type of masses they actually died. And so now we've considered essentially what the masses of the stars that actually produce these supernova explosions. You're probably the next question that comes to mind is essentially, well, how do these massive stars actually explode, right? How do we actually get what we observed? And so we're actually now kind of at a really great point in terms of studying supernovae because 3D simulations of this violent event is actually now getting to the point that one can actually make a massive star explode. But more importantly, they can actually start to try to make predictions of observables that we can actually start to test. And so, for example, they are actually predicting that there are large-scale asymmetries in the ejected metal distributions of these supernova explosions. They can make predictions for neutron star kick velocities that are now comparable with the velocities that we see in nature. And they can also predict what type of properties we expect to see from both the supernova and the supernova remnant. And so this is quite powerful, but what we can actually do is really now look at supernova remnants themselves and try to see if we can actually use these to try to test the predictions of these simulations to try to understand things about the explosions themselves. And in particular, we can try to take advantage of the fact that we see a large population of these super remnants in our local universe to really make statements about the general population of how stars actually explode. And so what we actually already know, right, is that when we look at, for example, the shapes or the morphologies of these objects, you can their core collapse origins or their origins of how they actually explode is already tied into their shapes. So visually, you can actually already begin to, without knowing anything about these objects, work out if something may have come from a core collapse versus, say, a type 1a supernova explosion, which I don't touch on in this talk today. In particular, we find that the core collapse supernova explosions tend to be much more asymmetric and elliptical in shape compared to the more type 1As, which tend to be much more circular and have more symmetric in shape. And so here I've given some examples of core collapse versus type 1A. So you can actually see that visually you can already actually do this in terms of understanding their general morphology. But what about the different elements, right? I talked only about what that looks like on the whole, right? Do we actually see some indication that, say, different elements we actually observed in a core collapse explosion, do we actually find that they actually show some asymmetry or differences between each other, between the different things? And so what do 3D simulations predict? Well, what they actually suggest is that actually the different elements in a supernova explosion, depending on their origin, will actually have different asymmetries. And so this is actually a really nice thing for us to actually go test. It's quite relatively easy to be able to do this. And so this is what we actually did. We looked at Cassiopeia A, or Cas-A, which is the youngest core collapse supernova remnant in the Milky Way. And what we actually did is essentially then took this beautiful image and we broke them up into their constituent elements, right? So here you can see we got the oxygen, magnesium, silicon, sulfur, calcium, argon, and iron, and even titanium. And what we actually did is essentially measured the morphology or measured essentially the relative symmetry or asymmetry of these objects. So are they more asymmetric? Are they more elliptical? Are they more circular or not? To try to understand exactly how the distribution of the elements actually change, particularly in this source itself. And so this is what Tyler Holland Ashford did, who's now actually a postdoc at Harvard. And this is what he actually found. And essentially, he was able to show essentially that how the different elements actually are distributed in terms of asymmetry or ellipticity. And so what we actually have here is that different elements are color-coded based on their different burning processes that actually produce these. But what the key part here is that here what we find is that oxygen, which is produced by helium burning, is very asymmetric, or sorry, very symmetric and very circular shape. We have the ones associated with mixed oxygen burning, us kind of in this intermediate part of associated of our diagram. While here we have magnesium that is produced in carbon burning, while here we have iron and titanium that is produced in explosive silicon burning. And so what this actually suggests by this plot is essentially that we have heavier elements are more asymmetric than, say, our lighter elements. And in particular, what we find, is that essentially oxygen in Cas A actually has a significant lower levels of asymmetry than the heavier elements. And while by comparison, magnesium has an asymmetry level that is distinct from oxygen, but is closer to that intermediate mass element formed through this explosive burning. While what we have here is essentially that iron exhibits the highest levels of ellipticity and mirror asymmetry. And so, yeah, essentially we have this. And so what this actually shows, or this is essentially clearly highlights, is that this is kind of one of the first times that it's actually been shown observationally that different elements, depending on their burning process origins, actually have different asymmetries in their explosions. And this is exactly what is predicted by 3D simulations. But we actually kind of try to quantify this more clearly. And so in particular, what the key takeaway of this plot is essentially that materials that are closest, or ejecta that is closest to the source of actually the explosion, will actually reflect the asymmetries that are inherited to the supernova mechanism themselves. And so you might think, oh, well, there's only one remnant, right? We pick Cas A. What about other ones? Well, this is currently a work in progress. We do see some similarities between these, but we also see some differences. And at the moment, Tyler is trying to kind of quantify these in a more in the best way possible to really understand the variety in the population that we actually see of some of the core collapse remnants that we actually observe in our local universe. So the next step, right, is essentially now kind of understanding, well, while we've looked at the ejecta, how they're thrown out into the environment, right, you're probably wondering also, well, you know, we know core collapse explosions also produce compact objects. And so is there a way that we can try to connect the core collapse explosion to the properties of the the properties of the compact objects that we actually see? And so we know that in supernova in supernova remnants, there are, usually this is kind of like the smoking gun signal for a core collapse explosion, and where it can be very easy to actually detect or know that something came from a core collapse because we can see the neutron star glowing at the heart of these beautiful objects. And in our local universe, we have about 70 supernova remnants that have a confirmed neutron star at the center of it. The other thing is that we do find is that apart from them sitting there glowing and they're interesting to be able to study in terms of their wind nebula and other aspects, that they also show kick velocities as well. And these kick velocities that we actually get are consistent with what we see kind of from general pulsars as well in our universe. So we know, for example, that we do see neutron stars have been kicked or are moving very rapidly through through the sky. Essentially, where here are some examples where we have one moving incredibly fast here, and then one kind of moving at more typical values. But what we can actually look at is essentially the distribution of those neutron star kicks, and what we find is essentially that it's described by kind of this very nice function here, where the mean velocity of most pulsars that we observe, both harbored within the neutron star and also ones that are not, or essentially isolated, tend to be around about 380 kilometers per second. And so when we see this plot, right, we know we've got neutron stars, right? The question that probably should come up here is, well, how do neutron stars actually get their kicks, right? Because we have this whole range of measurements we made, but they had to come from somewhere, right? Where did they actually do? And so This is where we can actually look at simulations of what they actually predict. And current simulations actually have two main predictions. So the first prediction is that hydrodynamic instabilities actually lead to kind of asymmetric mass ejection. And so what that would actually then predict is that essentially we would actually accelerate the neutron star in the direction opposite to the bulk of the ejector. And so this is essentially what we have on the left-hand side here. While if you considered another case where we particularly look at neutrino emission or anisotropic neutrino emission, what we would find is that in this case, this would actually carry away the bulk of the gravitational binding energy of the neutron star. And what that would actually then do is essentially both the neutron star and the ejector should move in the opposite direction to the majority of that energy. But what that would predict is that both the ejector and neutron star should travel in the same direction. And so with these two predictions, we can actually now essentially measure this, right? Because we know in our supernova remnants where the ejector is, we can see it. That's why they make these extended objects. And we can actually, for some of the pulsars, we can actually measure the proper motion and the direction of them. And so again, this is what we did with Tyler as well, where particularly what he did is that he looked at a sample of supernova remnants where we know the kick velocity, or where we can measure the proper motion and also measure the bulk asymmetries or the direction of the ejector's asymmetries. And what we actually have here is essentially shown in white arrow here is essentially the direction of the neutron star that we measured, while showing here in green is essentially the direction of the ejector that we measured from our analysis. And what this seems to suggest is that neutron stars are actually kicked by the supernova explosion in the direction opposite to the ejector. And so what is that actually consistent of? Well, that's actually consistent with essentially the first prediction that we had here. Essentially, it's consistent with conservation of momentum, that what our results seem to suggest is that at least for the ones we looked at, that some of the neutron stars that we see, their kick velocities come from just basic conservation of momentum, that has to go in the other direction. And so before I kind of get to the end of the talk, right, we have talked about neutron stars and like this, but you probably are also interested in understanding different types of neutron stars, because while we have 70 of these in our local universe, or that are associated with a supernova remnant, we actually find that each neutron star is unique and has different properties, but there is an exciting population of them, right, where they're called magnetar ones, where actually we do see both a magnetar associated with a supernova remnant. And in our local universe, so that's including Milky Way, SMC, and the LMC, there's about 37 known magnetars in these galaxies, and about 40% of them actually have quite secure supernova remnant associations. And so that's more than enough for us to try to understand, well, are these magnetars, which we know have very enhanced magnetic fields compared to, say, regular neutron stars, or compared to, say, compact central objects, right? Essentially, this now provides us an opportunity to work out, well, were they born in the same type of explosion, or are they unique in some way to be able to produce such an extreme magnetic field in this direction? And so what is our expectations? Well, if a proton-neutron star is born rapidly rotating, what we actually expect in this case is that would produce a kind of efficient dynamo in which magnetic field of this newly created proton-neutron star can actually then be amplified up to, say, 10 to the 17 Gauss, so consistent with what we find from these magnetar populations. And so as a consequence, what we would find is that a neutron star's with, say, initial spin down period of around 1 millisecond will then have a rotational energy of about 10 to the 52, which suggests that the explosion which produced these highly magnetized objects must actually be more significantly energetic than normal core collapse supernova explosions. And this is what kind of we find when we look at, say, superluminous supernova, which are thought to essentially be powered by these magnetar remnants. And so if you expect that they actually should be produced, these magnetars should be produced in these more energetic explosions, right, then as the magnetar actually spins down and evolves, right, we would then expect the magnetar to then power essentially the associated supernova, or even the supernova remnant itself. And so, like I said, it's been suggested that they power light curves of, say, supernova-related transients, such as long and short GRBs, superluminous supernova, and other ones. But in particular, right, we want to consider how it would affect the supernova remnant, because that huge energy reservoir associated with the magnetar explosion should not only just affect that initial transient where people detected in a transient survey, but really it also should affect the long-lived supernova remnant themselves. And so the question here is like, well, do magnetars actually affect their long-lived supernova remnants, right? That's kind of what we're going to test. And so what are the two predictions that we actually have here? Well, what we would expect is that the energy injected by the magnetar will then lead essentially the energy of the supernova remnant that we measure to then be dramatically exceed the canonical 10 to the 51 ergs that we expect from just this basic kinetic energy of the explosion. And then what we would then, if that's the case, right, then what we would actually expect is that the supernova remnants associated with these magnetars should be significantly extended compared to their supernova remnants of similar ages environments, because suddenly you have this extra power source that's pushing the shock front faster out into the environment. And so this is what we actually did to try to understand, or we actually kind of had a look. Oh, my slides have now seen. And then what we actually did is that, first of all, we looked at the shapes of this, and this is what we did with a undergrad student at Santa Cruz. We particularly looked at the sizes of these remnants and compared them to the sizes of other supernova remnants that do not harbor a magnetar and are also found in similar environments. And what the key plot here is that we find that really magnetar remnants are not significantly extended compared to other supernova remnants found in those similar environments, right? So, which seems to suggest that they're actually not much bigger than what we actually try to understand, or much bigger than what we actually expect. We can also look at, say, the morphologies of these magnetar remnants, and what we, because maybe, for example, we'd expect them to maybe be more asymmetric because they're coming from more extreme explosions, for example, or, there may be something different about them. And what we've essentially just plotted here is essentially we've just plotted the distribution of our of the different remnants where we actually have the measured how asymmetric they are or how elliptical they are, and highlighted in the red stars is essentially the magnetar remnants that we have associated with these objects. And in particular, what you can see here is that they have similar morphologies to the other core collapse remnants in our sample, right? They're not uniquely different to the other population, right? So what this seems to suggest to us is that actually they may be just born in similar explosions. And so this is, again, quite puzzling because we expect them to be different, but we can now look essentially again at the energetics of our magnetar remnants. Right, and in particular, because we said that if you have this extra power source, they should be much more energetic, say, than what a normal core collapse is. And again, we find that they do not deviate really that significantly from those of from this explosion energies that we estimate for supernova remnants that do not harbor a magnetar themselves. And so it seems to suggest that maybe this is not the case, right? That we actually finding that maybe they'll actually kind of be born or are created even in just normal core collapse explosions. There's not some other way. And so what we seem to suggest here is essentially that when we compare them to, say, superluminous supernovae or GRBs, where we're thought to actually harbor these magnetars or seem to power these light curves, what we suggest from our supernova remnant study is that they're actually under-energetic compared to what we find from, say, magnetar-powered supernova transients. And so what we seem to suggest is that maybe not all magnetars are born rapidly rotating, or maybe they don't actually all power superluminous supernovae. And so in this sense, just re-summarizing essentially that, yeah, we expect that maybe some magnetars, at least in our case, are actually just produced in normal core collapse supernova explosions, which then is an interesting question of, well, how do those normal ones then still lead to these extreme magnetic fields? And this is something that we're still trying to actually look into. And so here I'll just leave my summary slides up. Hopefully I was able to show that, apart from being very beautiful, supernova remnants are actually very good and very useful tools to try to connect to the end points of stellar evolution, essentially when stars die. And we can use them to try to probe a wide range of different properties or understanding of many aspects of stellar death, and in particular the mass of these supernova, how they explode and throw out their ejecta, and how essentially do their compact objects obtain their kicks, and whether they're rapidly rotating or not. So thank you so much.
Thank you. Thank you for your very nice seminar. I think we can take questions now. I can see various hands. Let's go one by one. Anna, can you please unmute yourself?
Can you hear me?
Yes, we can hear you.
Yeah, I had a question about the first part when you found that most of the progenitors needed to be heavier. Could that, or does that also imply that the initial mass function is more top heavy?
Very good. Yes. So you're particularly talking about this part here. So the SMC is very special because it's very, very low metallicity. And so this naturally leads to more massive stars, because in low metallicity environments, your winds are actually repressed, which means that you essentially keep more mass and more angular momentum closer to the star. So you can actually get larger stars in this. And so in that suggestion, it does look like it's more top heavy, but we did try to compare it to a Salpeter IMF. And we find that actually it's probably closer to consistent with a Salpeter, just a standard IMF, but the uncertainties are really large because we just can't constrain the values that we hear. But there is maybe a hint that in this galaxy it is top heavy. And this is why we went to a different galaxy to have a look. But we think within uncertainties, which are again very large, that it's still consistent with a Salpeter.
Thank you.
Luca, can you please unmute yourself?
So first of all, very, very interesting talk. And I also have a question about the first part. So at some point you showed the explodability as a function of initial mass of which stars explode and which ones don't. Yeah. So we published recently a paper where we show that if you try to use a different method to do the explosion, you basically find that between 12 and 15 solar masses, you don't get explosions, but you do get explosions between like 21 and 25. Which, some simulations of the Princeton group also find this. So I was curious if your method can be narrowed down to like smaller like mass ranges, specifically 12 to 15 and 21 to 25, because you say that you seem to find a lot of from these supernova remnants, a lot of stars exploding from 21 and above. But I'm curious what this and above means, where like can you narrow it down, for example, up to like 25, say, or?
So probably not necessarily in this method, because of the fact that the resolution of our star formation histories are limit to us to be able to say something is only a small, medium, or large massive star. But we can go to other methods to actually do this. In particular, we can actually measure the abundances of the ejecta that we see in the different core collapse supernova explosion, or in the supernova remnants, and then we can compare them to different models for the expectation of the nucleosynthesis yields. And in that case, we actually can get a little bit more accurate. So we do see in the population of supernova remnants that at least I have studied, and we're trying to do this in a much more comprehensive way, but there's a lot to get through. It's not an easy task. That we do see supernova remnants that have masses somewhere between 15 solar masses and up to 25. And, so for example, so in my PhD, I did supernova remnants. That's what I started off before moving more into supernova and trying to make this connection. I went to what led me to kind of start doing this a little bit more in this more broader context is that I went to a conference where we were talking to supernova people, and they said, we see nothing above 18 solar masses. And I went, that's kind of weird, because every time I measure the abundance from these remnants, I see things that are consistent with, you know, the things that they're not detecting, what is going on, right? That's kind of what led me to that. So we do see observable explosions. Unfortunately, our star formation histories in these galaxies are not good enough to be much more precise. You would be able to do it. I think they're trying to do a better survey of the LMC, SMC to try to get more comprehensive, more high resolution star formation histories. But I'm just using ones that were publicly available, right? And, you know, to do that type of study is pretty intensive. So I think in that method, we probably wouldn't be able to do it, but I think there are other methods we can actually try to attempt that. And that's something we're working on, but it takes a little bit of time to get there.
Thank you.
Young, can you please unmute yourself?
Yeah, hi. Okay, very nice talk. And I would like to have a clarification. Early on, you showed some diagram regarding the delayed time distribution for supernova. I'm a little bit surprised that it extends to 100 million years and so. These are all for core collapse.
These are all for core collapse, so I don't consider any type 1As in this study. But what we find is that there are a few papers that I tried to list at the bottom here that actually show that binarity can actually naturally affect your lifetime, similar with a low metallicity, because what happens is essentially you can better mix your nucleus, essentially your elements within the star, and so actually you can kind of refresh the core a little bit so they can actually go a bit longer. And so this is just the general distribution. You can see it falls off, but these papers at the bottom here that I highlighted have shown that actually, yeah, you can considering binarity, and we know, for example, that a significant fraction of stars are actually with a binary, they're not single stars, is that actually we do have to take into account that binarity is a big effect on the actual lifetimes of the stars. And the standard assumption of a single star, that all stars are kind of isolated, is actually probably not fully representative of the actual distribution.
Okay, thank you for that clarification. I have another follow-up question, but over to the morphology of these elements from different stages of burning. You know, you showed both iron and titanium, both coming from explosive burning. And regarding the morphology, the iron is much higher on the ellipticity, whereas the titanium is more circular. But these two tend to go together. You know, iron is made as nickel, titanium, they come together. Why the difference? It's a huge difference in terms.
It is a huge difference. Okay,
Yes.
so here's an image of it, right? The one sitting at the bottom of our plots here. So one thing is that titanium is not, so what we use here is the Chandra X-ray satellite, which allows us to observe between 0.3 keV and 10 keV, which essentially we could capture everything up to iron pretty well. But what we actually have for titanium here is actually that's detected with NuSTAR, which is a different instrument, and its resolution is not as good. So in that sense, we can't resolve the structure as well. But also the thing is that titanium is produced by radioactive decay, right? So it's probably that it hasn't fully, either we're missing a large fraction of it compared to what we see for the iron. And so we include it just for completeness, but actually we think we can explain why it's so different compared to the other parts. It's that we're just not capturing it in the same way that the other elements are.
Okay, thank you.
Susan?
Great. Thanks for the nice talk. I'd like to ask a question about the same slide Luca asked, but I would like to ask a slightly different question. So can you show it so I can show you? Okay. So my question is that I see so for example, if we pick this MZAMs of say about 30 or so, that as we scan across the core collapse explosion models, the outcomes are radically different. And so one question is, can we imagine that these different models could incur different properties in the supernova resonance, so that we, by analyzing some properties of them, we might be able to infer different outcomes for the explosion?
So yeah, that's what we're trying to do. So it's actually a really good question.
No, but yeah, so Luca asked a slightly different question. I guess my question is whether or not, I mean, how visible in regards to these outcomes, how would a supernova remnant associated with a W18 model would be different from N20 or S19.8? That's what I was trying to ask.
Yeah, so I don't know. I said I actually don't know the answer to that. The reason why is that these models correspond to only really understanding the supernova explosion, not the supernova remnants. To be able to get to the supernova remnants, they have to evolve these models to essentially, because these remnants are thousands and thousands of years old and depend on how essentially what environment they're exploding into as well. And so in this sense, they give a prediction maybe of what the light curves of the supernova look like, but there's not that many there's not as many right now of explosions or like models that actually then lead from these different parts of how essentially what the next part is to the supernova remnant. And so while we can try to kind of extrapolate that maybe they have a different energetics, which then would lead to different shapes of these, do we see these different masses or do we see neutron stars or not? We can do it in this way, but I think it's not at the moment, I think it's not as easy at the moment to do this, because I think the models is that here observations are significantly further, I think, compared to where the simulations are, just because it's very complicated.
So thank you very much for providing that connective tissue. So I appreciate that perspective. Thanks.
Anna has one more question, probably. Anna?
Yeah, we're using Anna's laptop to project this at UCSD. So this is George Fuller. Thank you very much for this nice talk. So back to this Tuggleter's slide here. The vertical, these different models, what are they? How are they different from each other? Are these different velocities? Are they different assumptions about a given mass progenitor's structure?
Yeah, so they've got multiple differences, but different ways that they actually try to explode, different explodability properties, different metallicities as well that kind of lead this. I can't remember them off the top of my head, but they do correspond to slightly different ways that they actually lead to the final explosion that they could then use for their prediction. The paper that this is from is a dense paper. There's about 70 pages of it, but they do try to consider different
if I just think about core collapse supernova explosion simulations, I mean, there are only a few groups, right? There's Young's group, there's the Oak Ridge group, there, etc. There's Fornax and Attenborough's group, and a couple other ones as well. So they all get, they all agree on some things and not on other things, of course. And so I'm just wondering if there's some particular simulation that's used here with different properties.
You mean for the comparison? So I just showed this as an example. I could absolutely have shown, in the sense, any of the other simulation predictions, but I just thought
rather dramatic difference from top to bottom here, from S19.8 down to W20, for example, in what happens in this sort of 20 to 25 solar mass range.
Yeah, 100%, right? They produce very different answers, right? And so we can't, from the supernova remnant perspective, we can't be that accurate. We can't actually say that like exactly something is in 22 solar masses or something. We can only give a range to try to understand how it would then do this. So in this sense, visually here, what I'm looking at that is just looking that, we do see some gaps as we get higher, right? Or the amount of observable explosions get lower is the thing. And I think that is consistent between all the different groups. Between the thing, of course, they have slightly differences based on the actual explosion properties, but the first step was just to see like what, do we see something that is consistent? And then the next step we can try to now think about is like, can we actually be more precise and then start to actually put more constraints to then connect to the type of explosion? Can we put constraints on metallicity? Can we put on the type of explosion mechanisms? And at the moment, I think it's not entirely clear. We're trying to work out ways that we can properly beat down the uncertainties of our masses.
I guess what's puzzling me really is what the uncertainties in the progenitor pre-collapse evolution gives to the final outcome.
Oh, I think it's huge. Is the answer. We get quite a
Maybe
few.
maybe that's what these different models are different.
Yeah, so I think it's connected to this. Yes.
Very good. Thank you.
Young, do you have another question? I can see your hand is there.
I forgot to roll my hand, so I'll lose it.
No
Sorry.
problem.
Okay. Yeah, thank you.
I think there are no further questions. There are already lots of questions, and thank you again for your very nice talk. And let's thank the speaker again, and we will meet next week. Thank you, Katie.
Awesome. Thank you so much for inviting me. Good to see everybody. Enjoy your night.
Yeah. Bye.
Thank you.
Bye,
Bye.
thanks.